Welcome everybody. This is our third class for module 2. So already we have seen what is buoyancy, what is center of buoyancy and the problems related to buoyancy and center of buoyancy. So we know when a body is immersed in a fluid, when a body is immersed inside a fluid, okay. So if the center of gravity is here, the buoyancy will lie here because the center of gravity, if the depth of the object is d and depth of the body immersed in the water is, we will take it as d1. That means our center of gravity will be equal to d by 2 and the center of buoyancy will be equal to d1 by 2. That is why the center of buoyancy is below the center of gravity. We saw this and we have solved a few problems based on the relation, that is the volume of the water displaced will be equal to the volume of the body submerged in the fluid. Also, the weight of the body in air minus weight of the body in water will be equal to weight of the water displaced. So these concepts we have seen already. Today we are moving on to the next concept, that is Metacenter. Okay, so our next concept is Metacenter. What is metacentric height? Or you can call it as Metacenter, metacentric height, and analytical method for finding the metacentric height and the problems related to this. So today we will see these three things. What is metacenter, what is metacentric height, and the analytical method. This is a derivation, very important derivation. Analytical method for determination of the metacentric height. And problems related to this we will see in the next class. So, first of all, we will see what is metacenter. Now, see this diagram. You can see this is the free surface of water. Okay, this is the free water surface. So, we have a water body and this is a body immersed inside the water. And G is the center of gravity and B is the center of buoyancy. That means the weight of the body acts downwards, the center of the buoyant force acts upwards. Okay, in other words, the weight of the body will act, both act along the normal axis. When the, this diagram is, this is the body is in equilibrium. Body in equilibrium. So when the object is, or when the body is in equilibrium, the weight of the body will be acting downwards along the normal axis and the buoyant force will be acting upwards along the axis, normal axis. So this is the normal axis for this body. Now, this body is in equilibrium. Now you are tilting the body. You are making the body unstable. Okay. So when you are trying to oscillate the body. See here, the practical example is the movement of ship. You know, the ship moves in water. And when you need to tilt the ship, when you need to move the ship, you need to give some angular displacement. Only then the ship moves forwards. So that is the reason you are studying metacenter and metacentric height and the concept related to this in fluid mechanics. Now, you are giving an angular displacement in this direction, that is in the clockwise direction. That means this angle is theta. You are giving an angle theta, you are giving a clockwise angular displacement theta along the normal axis. You are moving this normal axis in this direction. You are giving an angle of theta in clockwise direction. So that you call it as angular displacement. Now what happens is, because of this angular displacement, because the neutral axis is tilted. Since you are giving an angular displacement, your normal axis gets tilted in this direction by an angle theta. The normal axis is tilted by an angle theta. So when your normal axis is tilted, your center of gravity lies along the normal axis here, and the buoyancy, center of buoyancy is shifted from B to B1. Okay, center of buoyancy is shifted from B to B1. Now, the weight of the body acts vertically downwards. Weight of the body acts vertically downwards. At the same time, the buoyant force acts vertically upwards along, and the point of application of this buoyant force is along B1. It acts vertically upwards along B1. So when it acts vertically upwards along B1, this will meet at a point M. This force, this buoyant force will meet at a point M. So this point M is called the metacenter. Okay. So this point M is called the metacenter. Okay. So this is the concept of metacenter. Now this distance, see, distance between the center of gravity and the metacenter is called metacentric height. That is, GM is called metacentric height. Now we will define metacenter. So metacenter is defined as the point about which a body starts oscillating. You are tilting the body. Okay, so the body starts oscillating when the body is tilted by a small angle. Right? Now, so another definition for metacenter is, it is defined as the point at which the line of action of force of buoyancy will meet the normal axis of the body when the body is given a small angular displacement. So the point where the buoyant force meets the normal axis, that point is called a metacenter. Okay. Now, we will see what is metacentric height. We have seen it as the distance mg, right, or gm, that is the distance between the metacenter of the floating body and the center of gravity of the body. So, distance between center of gravity and the metacenter. This is called the metacentric height. So, gm is, g is the center of gravity, m is the metacenter. So, this gm is called, the distance gm is called metacentric height. Now, we will see how to find the formula. We are going to derive the formula for metacentric height. So, first we can derive this using two methods. First method is analytical method and the second method is experimental method. So, today we are going to see the derivation by using analytical method. Then we will solve the problems. Afterwards, we will go for experimental method. So, analytical method for metacentric height. See, the formula is GM. We know, see, already we have seen this GM is metacentric height. So, our formula is GM is equal to I by V minus BG. I is the moment of inertia. Okay. So, the moment of inertia about YY axis. GM is I by, I is the moment of inertia of the body about an axis. This V, see this inverted A, or this is V and you strike it, okay. So this is the volume of the body immersed in the water. It is nothing but the volume of water displaced. So moment of inertia by volume of water displaced minus Bg. Bg we know, center of B is the center of buoyancy and B is the center of buoyancy and G is the center of gravity when the body is in equilibrium. This is the normal axis. Okay, so this is the formula. Gm is equal to, that is metacentric height is equal to I by V, moment of inertia by volume of the water displaced or volume of the body immersed inside the water minus Bg. B is the center of buoyancy and G is the center of gravity when the body is in equilibrium. Okay, now we will move on to the derivation. We need to derive this. So you see, as usual I have explained you, this is the body is in equilibrium. G is the center of gravity, B is the center of buoyancy, and you are giving an angular displacement of angle theta. Okay, we are giving an angular displacement theta. So what happens is, this is getting tilted. Your center of gravity lies along the neutral axis or the normal axis, and the center of buoyancy B gets shifted from B to B1. Center of buoyancy is got shifted from B to B1. So what happens is, because of this shift, see, this is the free surface of water, right? This is the free water surface. Now, this A, B, C, D. A and B are the points on the surface of water and where the body, okay, on the body at the surface of water, that is A and B. So now, because of, you are giving an angular displacement, because of the tilt, this A gets shifted upwards. B comes down the free water surface. A goes up to the free water surface and B comes down the free water surface. So the corresponding point of A here is A dash and B dash. So these points on the water surface, after the body is tilted, on the water surface the points are taken as A dash and B dash. A goes upwards, B comes downwards. And because of this, there is a formation of wedge. Okay, two wedges. So this is the normal axis. So we have two wedges. This point is taken as O. We have two wedges, O A A dash and O B B dash. So two wedges are formed. One wedge is above the free surface of water and another wedge is below the free surface of water. Okay, one wedge, that is O A A dash, is above the free surface of water. O B B dash is below the free surface of water. Now, see, because of the formation of these wedges, this O A A dash and O B B dash, there will be an increase in buoyant force in right side. That is, there will be an increase in buoyant force in O B B dash. Okay, there will be an increase in buoyant force. Buoyant force, we know always it acts upwards. Okay, so DFB, you are taking this increase in buoyant force as DFB in the region OBB dash. Similarly, in the region OAA dash, it is going above the free surface of water. So there is a loss in the buoyant force. Here there is a gain, here there is a loss. Or here in OBB dash, there is an increase in buoyant force. OAA dash, there is a decrease in buoyant force. DFB, you are taking this force as DFB. Here it is increased, here it is decreased. Now, see, there is a shift of the center of buoyancy from B to B1, right? And due to this shift, your buoyant force will be acting in the along the new position of the center of buoyancy. Okay, so this is FB. Now, see, because of these wedges, I told you there are two wedges. So, DFB, DFB, one is gain, one is loss. One acts upwards, another acts downwards. So, equal and opposite forces. So, there is a couple. So along the wedges, because of the formation of the wedges, there is a couple. A couple is developed. Similarly, because there is a shift in the buoyant force, center of buoyancy from B to B1, there is another moment, that is FB into distance BB1. This force, this buoyant force, cause a moment along the normal axis. Okay, so two things are happening. One is because of the formation of the wedges, there are an equal and opposite buoyant force, a couple. One is gain and another is loss. So these two forms a couple. Now since there is a shift from B to B1, this buoyant force will develop a moment along the normal axis, and these two, that is this couple formed, that is the moment due to this couple and the moment due to this buoyant force will be equal. So using this principle, we are going to derive the formula for metacentric height. This is our concept behind this, principle behind this. Okay. Now, see what is the moment of this couple? dFb into the distance between these two. What is the moment of this force FB? FB into distance BB1. Okay. Now we will move on to our derivation. So this is the length of this object. So the length of the object is taken as L. Now, so all the things are explained, all the things in the diagram are explained. Now, so G is the location of center of gravity, this G. B is the location of center of buoyancy. B1 is the new location or new center of buoyancy, new location for center of buoyancy due to angular displacement. Now, the vertical line through B1 cuts the normal axis at M. This M is called the metacenter. Okay, the vertical line through B1. See, because through B1 there is a vertical line. A vertical line is drawn through B1. Because, see, your weight will be acting downwards. So, this buoyant force is always a vertical force. Okay. So, buoyant force act vertically upwards. But the center of buoyancy is changing. So, this buoyant force acts vertically upwards. It is extended, it will meet at the normal axis at the point M. So this is called the metacenter. Okay, M is metacenter and GM is the metacentric height. You can see this GM is the metacentric height. When the body is in equilibrium, you will not have any metacentric height. Okay. Now, the angular displacement of the body in the clockwise direction. You are giving an angular displacement. You are tilting the body to an angle theta in the clockwise direction. So what happens is a wedge-shaped prism BOB dash on the right of the normal axis is formed and a wedge-shaped prism AOA dash on the left of the normal axis is formed. Okay. On the left OAA dash and on the right OB dash. Now, this results in a gain in the buoyant force on the right side, DFB gain, and a loss in the buoyant force on the left side. This is the DFB, the downward direction. So these both together, these upward and downward forces, buoyant forces, okay? This upward and downward buoyant forces, equal and opposite. So these both together forms a couple. Now, these both together forms a couple. So the couple due to these buoyant forces DFB tends to rotate the body in the counterclockwise direction in order to keep the body in equilibrium. Now, the moment caused by the displacement of the center of buoyancy from B to B1 is also in the counterclockwise direction. Okay, because so you are tilting the body in the clockwise direction. So in order to bring the body to equilibrium, the forces acting will be in the opposite direction. Okay. So now the moment of couple due to wedges and the moment due to shift of center of buoyancy are equal. Okay, so the moment of couple due to wedges is equal to moment due to the shift of the center of buoyancy. So now you can see we are drawing this part, this wedge part once again. Otherwise, it will be so clumsy to see. So that we are drawing it once again. Okay, this wedge part is drawn once again. So now you are considering for derivation purpose, see all the things are explained except this dx. You are considering a small stripe of thickness dx in the portion OB dash. And this is at a distance of x from O. This dx is taken at a distance of x from O. Now see. So consider a small stripe dx at a distance of x from O. Now the height of this stripe, that is this height, okay, this height. Height of the stripe is, see when you have a triangle like this height will be equal to this distance into theta, if theta is small. So height of the stripe is x theta. Now area of the stripe is height into thickness. So height is x theta, thickness is dx. Now we know L is the length of the floating body. Then our volume of the stripe is area into length. So area is x theta dx into L. So the weight of the stripe is, you know, rho g into volume. Formula for weight is rho g volume. So rho g into volume, rho g, volume is x theta L dx. Now the moment of this couple for the stripe is, see weight is nothing but the force, right? So the force into distance. So the distance is x. So you are taking the small stripes on both the sides. So your couple acts between these portions. So force of this stripe. Okay, this is force of this stripe or weight. See force or weight. So the distance is 2x. So the couple is weight into 2x. Moment, sorry, not the couple. The moment is weight into 2x. Force into distance. Force into distance. Nothing but weight into distance. So you get moment is equal to weight of the stripe into distance between the couple. So weight is rho g x theta L dx. Distance between the couple is 2x. So you get 2 rho g x square theta L into dx. Now the moment of couple for the whole wedge. What is this? Is moment of the couple for the stripe. Now for the whole wedge you integrate it. So you get 2 rho g x square theta L into dx. Now this is our equation number 1, that is moment of couple for the whole wedge. Now moment due to the shift of center of buoyancy from B to B1 is shift of buoyancy is this FB into the distance, that is BB1. Distance with the normal axis is BB1. So FB into BB1, that is our moment. Okay, so moment due to the shift of CB from BB1 is equal to FB into BB1. So FB into BB1 is BM into theta. That is, you are taking this triangle. So you are taking this triangle. You have M here, B, B1, and this is theta. So BB1 is equal to BM into theta. Okay, BB1 is equal to BM into theta. So BB1 is equal to BM into theta. So this is our equation number 2. So 1 and 2 are equal. We get W BM into theta is equal to integration of 2 rho g theta x square L into dx. So what we get is 2 rho g theta into integration of, these are constants, integration of x square L into dx, we get W, see this theta and theta gets cancelled. So we get W into Bm is equal to 2 rho g into integration of x square L into dx. Now L into dx is the elementary area on the water line. You can see L into dx. What is L into dx in the diagram? See, this is L is length, this is dx, and this dx acts at a distance x from the normal axis. Okay. So we get, this is our area. This L into dx becomes our area dA. So W into Bm is equal to 2 rho g into integration of x square into dA. So you are taking this 2 inside in order to relate it with the moment of inertia. Because we have, this is our neutral axis, we have x on the right side and x on the left side. So it becomes 2x, 2 times. Okay. So now, see, 2 times this x square into dA is nothing but the second moment of area. dA into x square. X square into dA is the second moment of area. dA is the area, x into x. So second moment of area. It is 2. That is 2 sides of the neutral axis. So 2 into integration of x square into dA becomes your moment of inertia. So your W into Bm is equal to rho gi. Now Bm is equal to rho gi by W. We know this is the weight of the body. Weight of the body is rho g into volume of the water displaced. That is weight of the body submerged inside the water body. So it is rho g into volume of the water displaced or volume of the body immersed inside the water. So now you can cancel rho g. What you get is I by V. So Bm is equal to moment of inertia I by V volume. So we know Gm is equal to Bm minus Bg. You can see in the diagram. Okay. Gm is equal to Bm minus Bg. Gm is equal to Bm minus Bg. So what we get is Bm is I by V minus Bg. This is what is required for us. The metacentric height Gm is equal to I by V minus Bg. I is moment of inertia, V is the volume of water displaced. So this is very, very important. So thank you for today. From the next class, we will see a few problems on the metacentric height.